Good morning, everybody. Good morning, Ruben. Welcome to a Friday morning of Chem 1105 with your host, me, Dr. White. And good news, it's Friday. And for those of you thinking about it, you get Saturday and Sunday off from Chem 1105. And if you get withdrawal symptoms from Dr. White, not seeing me, go to my YouTube channel. All right. Let me go here. Let me do this. All right, thumbs up, people. Do you see Chem 1105 test 2 in blue on your screen? Thank you, Spencer. All right, let's go through this. I sent this out this morning, about a little past, about 20 to 8. And you should also get this as an email. A week from today, Friday, 10/15/21, I will be giving test 2 online during our Zoom meeting time next Friday. You'll be downloading a password protected PDF file for test 2 from the assignment area Blackboard, and that will be available on Thursday, sometime Thursday afternoon probably. And on Friday at 9:55, give or take a minute, I will send out an email via email, the password of the version, there's going to be 2 versions again, of test number 2 PDF file that you will take. You'll have until 11:30 a.m. to finish test 2 and upload your answers to the assignment area Blackboard as a single PDF file. And if we were doing this face-to-face, most students are finished about 40-45 minutes. My tests are never written that only 1 or 2 students out of a class of 24 are able to finish. I never do that. All right, important things. Test number 2 will cover chapter 4 and chapter 5, part 1. This will cover chemical bonding, including ionic and covalent bonds, and it will cover mole and mole-related topics, including balanced chemical equations. The test has 18 problems on 9 pages. Relax, it's designed for you to finish in a reasonable amount of time. This test, I have no multiple choice, but some of the questions are multiple part, like part A, B, and C. Now, point breakdown. For chapter 4 area, chemical bonds and related topics, there's 50 points. For mole and mole related topics, there's 55 points. If you notice, it adds up to 105. And what that means is there's five bonus points on test number 2. Now, the way I do bonus points, I do not put a super hard problem at the end, say that's your 5 bonus points. I just have the whole test add up to 105. Now, why is that bonus points? Because determining the number that I divide your total points by to get your percentage, I use for test 2 100 points, but it's possible, people have done it, to get 105. So there's five bonus points. Am I nice or am I nice? Don't answer that. All right. Now I will do a review of the material for test number 2 or on test number 2 in our Wednesday Zoom meeting next week. Now, this is something new and I should have put it in the first test, but I didn't. And I paid for it, unfortunately. Please note, If you do not upload your test number 2 answers as a single PDF file, I reserve the right to subtract 25 points from your test number 2 score. And if I do, you're not going to like it. I don't want to do it, but I don't have the time to play around with somebody who sends me 8 JPEG files, or I have to figure out how do I open this file. Make sure before you upload it, your PDF file, 1, you can open it. 2, it has all the pages of your answers. Every question is answered. Make sure you check that. Also, this is not an open notes or open internet or get anybody to help you test. That's called cheating. And if you cheat on this test, I will do what is in my syllabus. Trust me, I have things in test 2 that will tell me if you've A, gone to your notes, B, gone to the internet, or C, get help elsewhere besides your own mind. And by the way, have a great weekend. Gang Gesund. Best regards, Dr. White. All right, that's test number 2. Again, a week from today, you will receive that email with what I just read, and it's also available on Blackboard as an announcement. Oops. And anybody have any questions about test number 2? While you're thinking, I'm going to have some blueberry tea. Oh, is that good? Oh, it is. All right, let's move on. The material I'm going to cover now will be on test 3, not test number 2. On Wednesday, I was starting to talk about evaporation of liquids. And evaporation, as I mentioned, is the process and switches off for these definitions, but I'll be using them, so you should know what they mean. That's the process in which molecules escape from a liquid phase to a gas phase. In other words, molecules that are liquid become gas at a temperature where they'd normally be liquid. Now, temperature will affect that rate, and evaporation happens quicker for hotter liquids than colder ones. And I explained how your body cools you down. Remember, men sweat, women perspire. Is that sexist? I hope not. By the way, I learned not to be sexist very young age because I have 2 sisters, one 7 years younger, one 7 years older. Boy, I was in the middle, really. All right, I talked about cooling towers, and for those of you who want to stick around at the end of today's lecture, I will give my very exciting cooling tower story that saved my life, really. But that's optional, stick around. All right, now there's something we call vapor. And vapor is gaseous molecules, in other words, molecules that are gas of a substance, again, switches off here, at a temperature and pressure at which it would ordinarily be thought of as a liquid or solid. Right now, if you were to go outside, you'd feel the water vapor, we call moisture, in the air. The air outside of my house is at a temperature where water will not boil. Same thing with you. I hope it never gets that hot. We'd probably be dead then. Never mind, don't think about that. But anyways, that's vapor. Now there's something called equilibrium. Again, switches off. That's the condition in which 2 opposite processes take place at the same time. And in equilibrium, if you were standing up and you took 1 step forward, and right after that, you took 1 step back, and you kept on doing that, as a chemist, I'd say, oh, you're in equilibrium. Now in Chem 1211, I go into specific chemistry equilibrium, but I can tell you in your lungs and either your liver or kidneys, I always forget, chemical equilibrium are keeping you alive. Anyways, equilibrium is a forward and backward process that happens at the same rate. Now, vapor is a gas. All gases, you can measure pressure. And vapor pressure is the pressure exerted by a vapor above a liquid when the liquid and vapor are in equilibrium. Uh-oh, warning, warning, artwork by Dr. White. If you laugh too hard and break a rib, it's not my responsibility. If you have a beaker of water, some of the liquid is becoming a gas. And you're making water vapor, but when it's up here, it can go this way, making the vapor, but the temperature above the beaker is going to cool some. And the vapor pressure is the vapor above the liquid when the vapor and liquid are in equilibrium. That means as much liquid is becoming gas is when enough gas is becoming liquid. It goes back and forth. And we call the pressure of the gas right here, actually really vapor. You can measure the pressure with a gauge. So that's vapor pressure. Now, quick thing, I just thought I'd tell you, and this will never be on a test, what's something that's a volatile substance, such as gasoline? That's a substance that readily evaporates at room temperature because it has a very high vapor pressure. A lot of gases form quickly at room temperature, say, and it evaporates. If you were, and do not try this at home ever, if you put some gasoline on top of a surface, come back later, a couple hours, most of it will be gone because it's converted to a vapor, because gasoline is a volatile substance, meaning it has a high vapor pressure. It's also very flammable. Now, let's talk about boiling. And boiling is a specific form of evaporation where conversion from liquid state to vapor state occurs in the body of a liquid through bubble formation. So when you're boiling something, what happens? You form bubbles that are gas that form a vapor. And time for some show and tell from Dr. White. Time out for commercial.
My job is to make.
All right, let me start this again. This is water on a hot plate. Thumbs up, people. Do you see it on your screen? Maybe not. Thank you, Spencer. All right, let me start it again. There's no music or anything, so I'm going to narrate it. Notice these little bubbles forming. And I think you've all seen this when you boil water. What's in those bubbles? Water. But water is a gas, water vapor. And as it heats up, notice there are more bubbles. Dr. White's happy because it's pretty. I'm a chemist. I like this stuff. And notice the bubbles go to the surface and collapse. And above the surface, that means there's going to be a lot of water vapor. Wow, it's really bubbling now. Someone turn down the heat so it doesn't boil over. But anyways, this is what happens when you boil water. If you don't believe me, try it at home yourself. Now, there's something called the boiling point of a liquid. Switches on. I won't ask the definition, but you should understand it. I'll explain why. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the external, which we call the atmospheric pressure exerted on the liquid. So boiling point, which is a temperature, measures how much heat, and this is a Bunsen burner, you have to add to water. So the vapor pressure this way is equal to atmospheric pressure. One of these days I'll learn how to spell. Don't hold your breath. So vapor pressure is the pressure of water vapor if you're boiling water. And it's the same for other liquids too. And when this pressure, vapor pressure, equals that pressure, atmospheric pressure, the temperature of the water, if you had a thermometer, by the way, it's permitted to laugh hard at my artwork. That temperature, when the vapor pressure equals the atmospheric pressure, we call that the boiling point of a liquid. And at sea level, 760 torr, 1 atmosphere, the boiling point of water is 100 degrees C or 212 degrees Fahrenheit. Now, this is important. What is the atmospheric pressure? Oh, one other thing. Why did those bubbles rise? Well, they're about 1,000th the density of liquid water. And you learned about density. Things that are less dense go above a liquid or float on a liquid that's more dense, which is why those bubbles come to the surface and collapse. Now, normal boiling point, and I'll never ask you this, that's temperature liquid boils at 760 millimeters of mercury, 760 torr, 1 atmosphere, sea level. All right, I'm going to go through some stuff that's not in the book. Yes. All right. One of these days, they're going to make a webcam that's right in the center of my monitor, not on top over there. If I look like this, I can't look at what I'm doing. Dr. White will never be a TV announcer. Maybe not, nah. But anyways, if you ever go to Denver, you'll find out if you buy stuff, and I've had friends who live in Denver, and I've been there. If you buy something like noodles, which you boil for, say, 10 minutes to cook, there's a label on the package that says you've got to boil it longer. It doesn't say that, but it says boil for X minutes, which is more than what you would in Chicago. Why is that? Well, Denver is called the Mile High City. It's a mile high approximately from sea level. When you go up, and the switch is super on now, when you go up in altitude on our planet, the atmospheric pressure drops. So if I'm in Denver, that's going to be a lower atmospheric pressure than here in Chicagoland. By the way, I was raised and born in Chicagoland, other than when I went to get my PhD, which was in Michigan. I lived all my life and have lived here in Chicagoland. But anyways, so when you go higher altitude, lower atmospheric pressure, you need less energy to get the vapor pressure in equilibrium at the same pressure as the atmospheric. And lower energy means lower boiling point, which is why you have to cook it longer. Now, for those of you who know music, going to Kathmandu, and I'm not going to ruin your day and sing it. I forgot who wrote that. But anyways, back when I was back when I was in school, that sounds better. That was a very popular song, and also going to the Himalayas, everything. Everybody wanted to go to Tibet and everything. But anyways, that's a bad place, but it was a craze. If you go to Kathmandu or you climb the Himalayas, which are really high, the boiling point and Google never fails unless I haven't shared it with you. Well, it failed me now. Come on. All right, let's talk about Mount Everest because I can't find Himalayas. If you're in Chicago, the boiling point of water is about 100 degrees. We're right at sea level. If you go to Mount Everest, which is the tallest mountain, I believe, in the United States, water only boils, yes, 70 degrees C. So if you're cooking up there like your noodles or rice, you're going to have to cook it a lot longer because you're at a lower temperature. What is the reason for that? And you should know, the higher you go in the planet, higher altitude, and Mount Everest is way higher than Chicago. Let's see if I can find this. Mount Everest is 29,000 feet above sea level. Yep, that's way above sea level. Sea level would be zero. And that's why the boiling point and the water at the top of Mount Everest is so low. That's pretty low. So you should know, when you go higher in altitude, the boiling point of water goes down. And what is the reason for that? The lower atmospheric pressure. And because most of you are visual, I'll explain that one day what that means. instant slide. Oh no, it's time for Dr. White to be subtle. All right, once again, what happens to the boiling point of the boiling point temperature, or otherwise known as the boiling point of water, as you go up to, say, the Himalayas or Mount Everest, if you're really brave. Dr. White would never go mountain climbing. I don't like heights. I can tolerate them, but I don't like them. You're never going to see me mountain climbing. No way. But I respect and honor those who can and do. But anyways, the boiling point of water, as you go to higher elevation, decreases because the boiling point is determined when the vapor pressure equals the atmospheric pressure. And because as you go higher altitude, the atmospheric pressure decreases as you go to higher altitude. How many of you are familiar, and give me a thumbs up if you are familiar with pressure cookers? No one? Oh, I see one person. No, that's not what I wanted. Let's try this again. How many of you are familiar with pressure cookers? Give me a thumbs up. I see a lot of you are. How does a pressure cooker work? Good question. Thank you. It's just the opposite. A pressure cooker, you always have some liquid in there like water or something with a lot of water. When you heat it up, the pressure inside there builds up. That's why it's called a pressure cooker. And because it's a higher pressure, it takes more energy to get the water in there to boil. And when it does boil, it's at a much higher temperature, more energy, higher temperature. And the higher temperature you cook food, the quicker it cooks. If you were just put it in boiling water, that'd be 100 degrees. A pressure cooker, the temperature is much higher. How much, I don't know. Dr. White doesn't like pressure cookers because part of my research when I was in industry, and I actually worked on the bench doing it, was very high pressure reactions, and they're quite dangerous. And I realized pressure cookers aren't that safe, at least back then. I think they are now, but I still stay away from them. But you should use them. Don't, but anyways, that's my personal opinion. All right, so you should know when you increase the atmospheric pressure, temperature goes up of boiling point of liquid, pressure cookers. When you decrease the atmospheric pressure, the boiling point goes down, going to any high mountain, Mount Everest, Himalayas, or even Kathmandu. Thank you, Elena. Thank you very much. I didn't know that. See, Dr. White still has a lot to learn, and I'm always learning, which is part of a training of a PhD or anybody who's educated, I hope. All right, let's move on. All right, if you're reading the book, there's something that I'm switching the switch. Will this be on test to the full off position? Let's talk about volume and moles and somebody's name you've seen before, Avogadro's law. And what is Avogadro's law? And this is why 6.02 times 10 to the 23rd is called Avogadro's number in honor of him. The volume of a gas is directly related to the number of moles of gas when the temperature and pressure are not changed. And I'll show you later, this can be derived by something called the ideal gas law. But what this means is at STP and molar volume, what's STP? Standard temperature and pressure. Back when I was in college and we were protesting the Vietnam War, STP stood for Stop the Pigs. That was the name that was given to the police. It was quite a violent time then. Anyways, STP, standard temperature and pressure, temperature 273 K, and that's 0 degrees C and 1 atmosphere. Now at STP, 1 mole of gas equals 22.4 liters. Switches totally off previous slide and this slide. And that's what Avogadro discovered. And because of that, they were able to measure how many moles of things. Then they finally figured out how to do that for liquids and solids. But he was the first one, I believe, to come up with a relationship with a mole of something and a measurement, which is quite important. Dr. White is extremely happy. Let's talk about my favorite, really favorite mathematical relationship in all of chemistry. And that's the ideal gas law. What's that? Switches on. If I had a dial that I could turn to 10, I just turned it to 100. I stole that from the movie This is Spinal Tap. And the ideal gas law is an equation that includes the quantity of gas in the sample, temperature, pressure, and volume of that sample of gas. We're talking about this right here. PV equal nRT. What is that? Well, first of all, I better be subtle. Ooh, wrong color to be subtle. If I could write this larger, I would. Know this. PV equal nRT. Now, what is the ideal gas law? It's this mathematical relation. Pressure times volume equals N times R times T. Well, what are those? Well, pressure, P is pressure. Now, the units, their different values are critical. Wrong units, PV equal nRT won't work. Pressure always has to be in atmospheres. Volume always has to be in liters. And on a test, I'll always give you liters. N is the number of moles, but I've never seen a balance in moles, but grams, and you're going to have to convert those to moles, which you learned how to do. And temperature, always for ideal gas law, has to be in Kelvin, but all thermometers are in degrees C in chemistry. But you know, whoops. Unwhoops. Kelvin equals degrees C plus 273. And finally, what's this R? R is called the universal gas law constant. See, I even have this on a slide. And the universal gas law constant we use in chemistry is 0.0821, and its units are atmospheres times liters per mole K. That's the units of R. Now, good news, in the past, students had to memorize this. No more. This will be given to you, PV equal nRT, and what PV, NR, and TR, and also I'll give you the actual number value. Now, R is the actual calculated value. And because of that, this one that I use is 3 significant figures. Best you wouldn't have guessed that. But I've seen on a website, and I don't know who would need it, but I guess somebody did, or somebody felt like calculating R to, I think it was 12 or 15 significant figures. I wouldn't use it, but somebody needed it. And that's PV equal nRT, the ideal gas law. Now, interesting thing, where in your daily life is there gas? Well, you can say the air you're breathing, but where else is it important? Your car tires. And PV equal nRT gives you important information about your car tires. Now, long ago, when was this? I just thought it's probably before most of you were born. But anyways, here in Chicagoland, I think it was about the mid 1990s. How many of you were born after 1996? Give me a thumbs up. Oh, I should. I shouldn't have asked. Well, anyways, at that point, I hadn't bought my house yet that I'm living in now. I didn't have a garage. I lived in an apartment complex, which was quite nice. There were a lot of nice people and we partied hard. But anyways, 1 week on a Friday night, temperature got super cold, like about 12, 15 below 0 Fahrenheit. That's not the wind chill. And I have, for many years now, I've owned Ford Explorers. I like them. And this was parked outside in the parking lot. I figured, Saturday morning, I can get up early and start my car, drive it around, warm it up. And that also helps keep your battery charged. Well, anyways, it's about 7:30 in the morning. Dr. White's a morning person. It's like 10 below outside and it's cold. And luckily I have the gear to go out in cold weather. I go to my Explorer, I look at the truck, I look at my tires, oh no, I've got 4 flat tires. Then it took me about, almost 2 whole seconds. Finally, this part of my brain saying, wake up, that's PV equal nRT, you know better. What do I mean by that? Well, let me show you. By the way, hint, wink, wink, hint, hint, say no more. Know this. PV equal nRT. What that means is it's always true. This side, whatever number you get, is always equal to that side. Well, in your car tires, PV equal, it should be a lowercase n. In your tires, this is a constant, universal gas law constant. So that should be constant. And in your tires, unless you get a flat, and I hope you don't, they're not fun, should be in your tires. And volume in your tires, also, unless you get a flat, is a constant. So if we look at this, V, N, and R are going to be constant. But in the winter, like that morning, what happened? The temperature was way down. Well, if the temperature goes down, then the only thing on this side that can change is the pressure. And what I saw was, and what my brain finally kicked in and said, PV equal nRT, in the winter, when the temperature goes way down and your gas in your tires get cold, the pressure in your tires goes way down. And it looked like I had almost flat tires. They weren't totally flat, but they were sure not good looking. And immediately I got in my car. And back then, not far from where I live, there was a gas station that had free air. That's getting rare and hard to find these days. Back then it wasn't. And I went and started filling my car tires, all four of them. And by the time I'd inflated them, filled them up with more air, so now the pressure would be higher at this lower temperature to make PV equal nRT true. I looked up and I saw about 10 other cars waiting in line. And I bet a lot of people use that compressor. Ooh, you know how a compressor works. So in the winter, when the temperature goes down, your pressure of your car tires will go down. And why? PV equal nRT tells you that. V, N, and R are constant. In your tires, but if T goes down, then the only thing that can change on the left is the pressure, and that's going to go down. So in the winter, you should keep an eye if your car's been out and super cold, keep an eye on your car tire pressure. I check mine religiously once a month. I have an older car and I don't have the gauges in my car. I have a gauge that you stick on the tire. Now, back about a year, or let's see, I think this happened. I'm off on my date. That probably was the late 1989, 88. This cold weather happened. There was some cold weather back then. Still, we get cold weather every once in a while. Now, back in about 1995 or 96, I forgot which, in the summer, we had a brutal summer. I mean, brutal, deadly. Temperature for 2 weeks, the daytime temperature was over 100 every day for 2 weeks. Back then in Chicago, this was before they had the concept of cooling centers, over 500 people died because of the heat-related issues. And if you drove around, and back then I used to work in Gurnee, so I had a long commute, almost an hour each way. If you drove around on the interstate, you would see cars and trucks pull over, lots of them, with their tires blown out, one or more. Why is this happening? Well, PV equal nRT taught us why. And back then, I was smart enough to keep an eye on my car tires. What happens in the summer when it gets real hot? The temperature goes up. Now, PV equal nRT, and you should know this too. In your car tires, V, N, and R are constant. In your car tires. Unless you get a flat, then, well, all bets are off. So if the temperature goes up, The only thing on the left that can change, the pressure will go up. So in the summer, temperature goes up, the pressure in your tires will go up. Why? PV equal nRT, the ideal gas law. And that's your friend. And if you were driving around, you saw a lot of cars with their tires blown out. Why? Well, if you blow a balloon too much and the pressure gets bigger and bigger, pop, it blows up. And that's what happened to those tires, especially trucks. I had a lot of trucks pull over. It was not a fun time either. Speaking about time, I'm just about done for today, but what I'm going to do is end 2 minutes early and let you who don't want to stick around for an interesting story go and run away. If not, the rest of you can stick around. I'm going to do my goodbye, but stick around if you want to hear a interesting story. And with that, I'm going to say, Gang gesund.